Building Automation Systems. Welcome to our session on Building Automation Systems, BAS. In this presentation, we will explore how BAS integrates essential building functions to improve energy efficiency, reduce operational costs, and enhance occupant comfort. Let's dive into the components, systems, and strategies that make modern buildings smarter and more sustainable. Topics to be covered. Define what a building automation system is. Review the main terminology and components of a building automation system and HVAC system. Identify common energy conservation measures for lighting and HVAC, boilers and water heaters. Maintenance. Let us see in detail. Building Automation System, BAS. Building Automation Systems, or BAS, serve as the backbone of modern smart buildings. They integrate crucial systems like HVAC, lighting, and security into one cohesive interface. This integration leads to improved energy efficiency and heightened occupant comfort. By automating routine tasks and adjustments, BAS significantly lowers operational costs. Additionally, BAS continuously collects data to monitor building conditions, facilitating optimization of energy usage and supporting sustainability initiatives. Energy Management System, EMS. An energy management system is a vital component of BAS, focusing on tracking and optimizing energy consumption. EMS enables real-time monitoring of energy usage, identifying patterns and inefficiencies. It highlights opportunities for energy savings, helping to lower both costs and carbon emissions. By utilizing data analytics, EMS adjusts settings based on current usage trends to ensure optimal energy distribution. Regular monitoring and reporting empower facility managers to adopt proactive energy conservation strategies. Parts of Building Automation System. A building automation system is composed of several key components, including sensors, controllers, output devices, and a user interface. Sensors gather vital data such as temperature, humidity, and occupancy levels to inform system operations. Controllers process this data to make informed decisions, adjusting various systems accordingly. Output devices, like valves and dampers, act on commands from the controllers to regulate conditions. Finally, a user-friendly interface provides facility managers with centralized control over all building systems, enhancing operational efficiency. Temperature and occupancy sensor. Temperature sensors are essential for maintaining comfortable indoor environments by measuring the temperature of specific areas. They enable the HVAC system to adjust automatically, ensuring optimal comfort levels are achieved. Occupancy sensors play a critical role by detecting whether a space is occupied, triggering systems like lighting or HVAC only when needed. This dual function helps reduce energy waste significantly, as systems deactivate in unoccupied areas. Proper sensor placement is vital for maximizing their effectiveness and energy conservation efforts. Building controllers act as the central hubs of a BAS, integrating data from various sensors to make operational decisions. They are responsible for sending commands to output devices, adjusting heating, cooling, lighting, and ventilation systems. Controllers can be programmed with specific settings tailored to the unique needs of a building, enhancing efficiency. Their ability to communicate with other building systems fosters a more integrated approach to building management. A well-functioning controller ensures that the BAS is both responsive and efficient in real-time operations. Output devices and communication protocol. Output devices are crucial for executing the commands sent by building controllers, managing components like valves, dampers, and relays. These devices directly influence the operation of HVAC and lighting systems based on controller commands. Communication protocols, such as BACnet and Modbus, facilitate data exchange between all components of the BAS. They ensure that various devices can work together seamlessly, enhancing system compatibility and integration. Reliable communication is essential for maintaining the overall efficiency and effectiveness of the building automation system. Terminal or user interface. The user interface is the gateway for building managers to oversee and control the BAS functions. It provides real-time insights into system performance, energy usage, and environmental conditions within the building. This centralized platform simplifies the management of complex systems, featuring user-friendly dashboards and alerts for any irregularities. Customizable settings allow managers to tailor controls for different building zones, enhancing operational efficiency. An intuitive interface fosters greater engagement from users, promoting more effective building management. Air handling unit. Air handling units, or AHUs, are essential components that distribute conditioned air throughout the building. They incorporate various elements, including filters, fans, and heating or cooling coils, to manage indoor air quality and temperature effectively. BAS controls AHUs to optimize airflow based on occupancy levels and temperature settings, ensuring energy-efficient operation. By maintaining optimal conditions, AHUs contribute significantly to occupant comfort and well-being. Regular maintenance is crucial to ensure their reliability and to sustain performance over time. Chiller. Chillers are critical systems used to remove heat from the building, especially in large commercial facilities. BAS monitors and controls chiller operations to adjust cooling based on real-time demand, ensuring efficient energy use. By integrating with other building systems, chillers can operate in harmony with HVAC and lighting controls, further enhancing overall energy efficiency. Regular maintenance and monitoring are essential to ensure optimal performance and longevity of chiller systems. Cooling tower. Cooling towers play a vital role in dissipating heat from water-cooled HVAC systems, enhancing chiller efficiency. BAS manages the cooling tower's fan speed and water flow based on real-time ambient conditions, optimizing performance. Properly controlled cooling towers significantly reduce both water and energy consumption, making them essential in energy-efficient buildings. Their effectiveness is especially pronounced in hot climates, where cooling demands are higher. Routine maintenance of cooling towers is crucial to extend their operational lifespan and ensure efficiency. Flow controller. Flow controllers are devices that regulate the flow of air or water in HVAC systems to maintain balanced distribution. They ensure that energy is used efficiently by adjusting flow based on real-time demand, preventing both overheating and overcooling. BAS plays a pivotal role in managing these flow controllers, optimizing their settings for stable temperatures. Effective flow control reduces strain on HVAC systems, extending equipment lifespan and enhancing overall comfort. Properly managed flow controllers are key to achieving optimized performance in heating and cooling systems. Boiler. Boilers are essential for generating hot water or steam used for heating in large buildings. The BAS manages boiler operations to adjust heating output according to outdoor temperature and current building demand. This efficient control helps minimize fuel consumption and greenhouse gas emissions, promoting sustainability. Monitoring the efficiency of boilers is vital for ensuring effective heat delivery without wastage. Regular maintenance of boilers prevents malfunctions, ensuring reliable operation throughout the heating season. Dual duct. Dual duct systems provide both hot and cold air streams to maintain consistent temperatures across different building zones. BAS regulates the mixing dampers within these systems to achieve precise temperature control, optimizing energy use. This flexibility allows for meeting diverse space requirements effectively, catering to varying occupancy patterns. By minimizing heating and cooling loads, dual duct systems contribute to lower energy costs. They are particularly beneficial in buildings with fluctuating usage patterns, enhancing comfort and efficiency. Hot and cold decks. Hot and cold decks store preconditioned air, ready for distribution based on specific temperature demands in various building areas. The BAS manages these decks to balance heating and cooling efficiently, reducing energy usage. By supplying only the necessary conditioned air, this approach helps achieve substantial energy savings. The ability to make rapid temperature adjustments improves overall occupant comfort. Regular monitoring of deck temperatures prevents imbalances that could lead to energy waste. Variable air volume, VAV. Variable air volume systems are designed to adjust airflow based on the specific demands of each zone, ensuring optimal air quality with minimal energy use. BAS controls VAV boxes to modulate airflow in response to temperature settings and occupancy levels. This system enhances energy efficiency by eliminating unnecessary heating or cooling, particularly in office environments. VAV systems are favored for their precision in climate control, improving comfort for occupants. Consistent monitoring by the BAS ensures system responsiveness and efficiency. Terminal reheat. Terminal reheat systems adjust air temperatures closer to the point of delivery, providing enhanced control over individual zones. The BAS fine-tunes reheat levels to meet occupant comfort needs while keeping energy usage to a minimum. This system is particularly effective for spaces that experience varying temperature requirements. Efficient control of terminal reheat helps reduce overall heating and cooling loads, contributing to energy conservation. Regular maintenance ensures that these systems perform consistently and effectively. Photoelectric sensor. Photoelectric sensors are crucial for detecting ambient light levels, allowing the BAS to adjust artificial lighting accordingly. By responding to daylight availability, These sensors help reduce unnecessary energy use in well-lit areas. This capability minimizes overlighting, contributing to lower energy costs and enhancing the building's sustainability profile. Proper installation and calibration of these sensors are essential for maximizing their effectiveness. The strategic placement near windows or skylights improves system responsiveness to changing light conditions. Scheduled start/stop. Scheduled start/stop functionality is a powerful feature of BAS, allowing for equipment operation times to align with building occupancy schedules. This prevents heating, cooling, or lighting when spaces are unoccupied, leading to significant energy savings. By limiting run times, this feature also helps to extend the lifespan of equipment, reducing maintenance costs. Scheduling can be easily adjusted for special events or holidays, providing flexibility in management. Overall, this simple yet effective tool enhances energy management strategies. Lighting control system. Lighting control systems play a vital role in adjusting lighting intensity based on occupancy and daylight availability. BAS can automate these adjustments or allow for manual scheduling, optimizing energy use without compromising visibility. By significantly reducing operating costs, these systems contribute to broader energy conservation efforts in commercial buildings. Dimmable lighting options and automated controls improve occupant comfort by ensuring adequate light levels. Proper configuration and maintenance of these systems are essential for maximizing their benefits. Economizer control. Economizer controls utilize outside air for cooling whenever conditions permit, thereby reducing reliance on mechanical cooling. The BAS automatically adjusts dampers to optimize economizer operation based on real-time temperature and humidity levels. This method is particularly effective in moderate climates, offering substantial energy savings. By managing economizer use properly, the BAS enhances indoor air quality while minimizing HVAC load. Routine checks are essential to ensure the reliable function of economizers and to maintain overall energy efficiency. Night purge ventilation. Night purge ventilation is a strategy that uses cooler nighttime air to naturally cool buildings, reducing daytime cooling demands. The BAS schedules this process, ensuring that fresh air circulates during off hours when temperatures drop. This not only lowers energy consumption during peak hours but also enhances indoor air quality. By implementing effective night purge strategies, facilities can achieve substantial energy savings while ensuring comfortable daytime conditions. Regular monitoring is crucial for optimizing this process effectively. Demand-controlled ventilation, DCV. It is a ventilation system that adjusts the amount of fresh air intake based on the occupancy level. The ventilation demand is determined by CO2 level, ppm. Higher occupancy leads to higher CO2 levels, triggering the system to increase fresh air intake. Lower occupancy leads to lower CO2 levels, triggering the system to reduce fresh air intake. This system helps maintain a comfortable and healthy indoor environment. Air damper. Air dampers are vital for regulating and directing airflow within HVAC systems, balancing air distribution across different building areas. The BAS controls these dampers to optimize the airflow based on real-time demands, enhancing comfort and efficiency. Properly managed dampers help to prevent issues like hot or cold spots, ensuring uniform climate control. Their integration into the BAS allows for automated adjustments, improving overall system performance. Regular inspections ensure that dampers operate correctly, contributing to effective air management. Variable frequency drives, VFD. Variable frequency drives, or VFDs, are essential for controlling the speed of motors in HVAC equipment, allowing for precise adjustments based on real-time needs. The BAS optimizes VFD settings to align motor performance with varying demand, resulting in significant energy savings. By reducing energy consumption during low-demand periods, VFDs help extend the life of HVAC equipment. This technology not only lowers operational costs but also contributes to sustainability goals. Regular monitoring ensures that VFDs operate effectively and efficiently. Chilled water system. Cooling tower. The cooling tower is responsible for cooling the water that is used in the system. Water chiller. The water chiller is responsible for cooling the water to the desired temperature. Chilled water pumps. The chilled water pumps circulate the chilled water throughout the system. Air handling unit. The air handling unit is responsible for blowing air over the heat exchanger, which cools the air. Heat exchanger. The heat exchanger is where the chilled water and the air meet. The heat from the air is transferred to the chilled water, which then goes back to the cooling tower to be cooled again. Cooled air. The cooled air is distributed to the building to provide a comfortable environment. Thank you for your attention. For more details, please contact TSD Office Engineering GHG. We appreciate your interest in ESG initiatives.